waving to the, there we go. So welcome to the Center for Transportation Studies Friday Transportation Seminar. Today we're very pleased to have Scott Samuelsen from University of California, Irvine to talk to us today about powering the future of transportation. Scott is a professor in the Mechanical and Aerospace Engineering Department, director of the Advanced Power and Energy Program, and the National Fuel Cell Research Center. And Scott today is a visiting faculty member brought by the OTREC program. So with that, we'll turn it over to Scott.
It's a pleasure to be here and very nice to have you go through the introductions. Helps me to understand where you're all coming from, and pleased to have both students and faculty and retired faculty and members of the community representing industry here as well. Probably the first step that we need to take is to get the slide up on the screen. I know that it's appropriately cued.
Let me, I thought is it your laptop? Did you have it before? Sorry.
I wouldn't do that again. It's already here, so I think I have it ready to put on the screen.
Let me go get this guy, sorry. One end out, turn things off, turn them back on again.
Thank you. So as you see here, the title is Powering the Future of Transportation. I want to begin by looking just at the automobile as we have it today, operated by fuel and air, combustion, taking that chemical energy in the fuel, transforming it into thermal energy, driving pistons, and then being able to provide propulsion. So watch carefully, there's the propulsion. If you don't mind, let me repeat that. I like that so much. There it is. But basically in a box, what we're doing is to take fuel and air in order to drive the engine forward. And it does give rise to what we want from an engineering point of view, the thermal energy, but it also gives rise to exhaust. And we have these species in the exhaust, which include the major products of combustion. CO2 is the species that leads to greenhouse gases, and then small amounts, but nonetheless very powerful amounts of pollutants that give rise to urban air pollution, which we generally call smog. To put this into the context of our natural resources, this is the Earth, and then that little sphere on there is the volume of air available to us on Earth. So that's what we're trying to protect for our own public health, and that's what we're contaminating with the exhaust to give rise to these environmental impacts. Another aspect of that air that we often don't think about is right here, which is the processing of air while we consume a tank full of gasoline. A tank full of gasoline for 20 gallons is about 160 pounds, so about a body weight. And a good question for us is how much air do we process when we go through a tank full of gasoline? It happens to be quite a bit. It's a ton of air, 2,000 pounds. Now of that, as we know, most of that's nitrogen, but not all of it. It means that we are removing from the atmosphere 400 pounds of oxygen, with every tank full of gasoline. And we have to ask, at what time will Mother Nature say, I can no longer replenish the atmosphere with that oxygen? Let me leave that question simply hanging. But for the moment, we do use combustion for producing power. In fact, 80% of the world's power is from combustion. 94% of the world's carbon dioxide, the principal greenhouse gas, is from combustion. And 90% of the world's criteria pollutants come from combustion. We're tending to move toward a greater utilization of combustion. Here's a plot of the amount of energy that we are consuming globally in the year 2000 and 2030. And one thing I want to represent here is simply the increase that we're going to be experiencing as now projected over the next 30 years. But I also want to indicate here how this is proportioned to transportation of interest here and to electric power. Both of those constitute the majority of our energy demand. Directly correlated to that is the carbon dioxide emission, or the greenhouse gas intensity. You can see they follow 1-to-1, going upwards by 2030 and having a contribution from transportation and electric power. That additional carbon dioxide is starting to tell a tale. And we see the tale now being represented by the media. This is my first evidence of a major news weekly stating that we have a problem. You can't see it, but this is April 2006, so about 3 years ago, almost to the day, when Time magazine said we should be worried, we should be very worried with respect to global warming, the impact of CO2. So that's becoming a forcing function, forcing change. Greenhouse gas intensity, first really identified by the world's community as an issue not even 20 years ago today. A second forcing function goes back to the early 1940s when smog was first identified in the Los Angeles area, and a few years before that, the London episode with respect to coal particles and fog. A third forcing function is what I'm going to call the Hubert's curve. This is actually very interesting with respect to driving industry to look for a different way of doing business in the oil industry. Hubert's curve is a plot of the petroleum production rate as a function of year. And what this says is what we would expect is that as we go through the years, we're tending to want to produce more and more oil. But what this also shows us is that there's a peak right here. It turns out to be at about 2020, where the discovery is going to be less than what we want to produce. This is now recognized within the industrial community, particularly the petroleum community, as being a reality. It's just an argument as to whether it's 2015 or 2022, but that's within basically the next 10 years, and is a forcing function to say we can't have this continuing dependency upon oil as our mobility fuel. A fourth and a fifth both came about due to 9/11, fuel independence and national security. So these are forcing functions doing what? They're leading to some very interesting and powerful paradigm shifts. I list them here. There are others as well, but we go from electric power, transportation, push toward conservation, building design, urban design. Many of you are engaged, maybe all of you are engaged in these areas. As an example of a response to one of these forcing functions, global climate change, greenhouse gas intensity, is in California, AB 32. And you have something very similar going on in Oregon, although in California this is law. This is law, which states that by 2020 we must reach these levels of CO2 emissions that we had in 1990. So that represents a 30% reduction from what we're currently projecting in not so many years, 11 years. And the California Air Resources Board, who's responsible for having this be accomplished, is just now embarking on the regulatory aspects that are going to be needed to reach that goal. Now, if you've been studying global climate change, you know that's an important step. You also know that's a remarkably large reduction for a state which is very much anxious to use its energy as much as it can. But it's not enough. We have to go further than that by 2050 to really make our contribution to bringing the greenhouse gas intensity to a level of reasonable state. Now let's take that background and focus in today's presentation on these two topics. I'm going to emphasize transportation, but we're going to end up talking about a nexus between transportation and electricity. As a result, I put all of that into the box. And I want to come back first to this diagram that we've just discussed at the beginning and start to work through it as to what changes we're making in this area by way of paradigm movements. Here we have combustion, which is taking a fossil fuel and through a variety of steps transforming it into electricity. We have the combustion, the thermal energy, and then that thermal energy expands, drives a piston, and turns a generator. Now I want you to be thinking from a transportation point of view of a Prius, of what we're doing in a Prius with the combustion engine to produce the electricity that then drives an electric motor and propels the vehicle forward. But we also do this to create the electricity in this room to a large extent. And we have these results that we alluded to earlier. You can almost feel intuitively from this sequence that there's some challenges that we've had to address over the years. Combustion leads to the formation of these criteria pollutants. In the combustion science community, we've done a remarkably good job to reduce the pollutant emissions from automobiles, from power plants. We've gone as far as we can, and yet it's not enough. And then you can see there are these processes that almost cry out inefficiency and metal moving against metal. They give rise to relatively low overall efficiencies in the transformation of that fuel to electricity. What's going on is a substantial emphasis to look for a combustion alternative. And what's emerging is the technology of fuel cells, where in one step we go to electricity through something that's called electrochemistry. No combustion, so no formation of criteria pollutants. And you can almost intuitively feel no metal on metal, so relatively high inefficiency, and in fact it is. The other attribute is it's relatively low in noise. It's basically benign, no acoustic emission, almost to a fault. It's hard to convince you that it's actually working because we're so used to cranking and chugging and metal on metal. So let's talk a little bit about this so that you can appreciate what it is that we have in our future. This is a fuel cell representation. There are three layers here. This green one is called an anode. The blue one is called a cathode. And that kind of orange in between is an electrode. Fuel comes into the anode, as you see here, hydrogen, and it reacts at the surface to form a proton and some electrons. The electrolyte says, proton, I welcome you, come on through. It says, electrons, get out of here. You're not going to come into my space. And sends them through another path, which for us is good because that path is a circuit where we can drive a load. And then the electrons come back to the cathode side, ionized oxygen that's coming in, and then that ionized oxygen combines the proton to produce the product of water. There are different fuel cell types. They vary in the electrolyte, they vary in the temperature of operation. And here I show you those different types. This is the proton exchange membrane fuel cell. You may not be able to see it, but it operates at about 100 degrees Celsius. All right? And that's the go-to fuel cell for the automobile. The reason is that it doesn't operate at that high a temperature, and it's a fuel cell that you can turn on and off, which we want to do in an automobile. These fuel cells up here are bigger, and they operate at higher temperatures. This is a phosphoric acid fuel cell that operates at 200 degrees Celsius. Takes about 3 to 4 hours to get started once you turn it on. Molten carbonate fuel cells, 650 degrees Celsius. Takes about 8 hours. This is now very popular in the marketplace. We call them advanced fuel cells, high temperature fuel cells. And there's quite a bit of development going on what's called solid oxide, which we often state is a holy grail of fuel cell technology for stationary applications. That will operate at 1,000 degrees Celsius. In the next year, we expect to see the first deployment of a commercial system. So these three are stationary fuel cells for electric power generation. And then down here is the proton exchange membrane fuel cell for the automobile. I'm going to focus on the PEM for the moment, and then I'm going to come back to the large fuel cells because there's a connection between the stationary fuel cells and our transportation requirements in the future. So on PEM, let's go back to the automobile operating on combustion. Let's just start by replacing the gasoline with hydrogen. But first I want to point out that the automobile efficiency is 16%, which means that 84% of the energy that you pump into your gas tank is thrown away to heat. So you pay your gasoline the next time of $30, multiply that by 0.84, and that's the money that's not going to be used at all to get you from point A to point B. Here's the 2,000 pounds of air that's required to process the tank full of gasoline. Now, the fuel cell future likes to operate on hydrogen, so we are looking to hydrogen as being the fuel. It has quite a few attributes on this chart. One is that the carbon-containing species here in the pollutants go away, and then the greenhouse gas here goes away, at least with respect to the automobile operation. If we replace the combustion now with a fuel cell, we up the efficiency a bit, quite a bit. And that's one of its attractive features going forward. That reduces the amount of air required per 400 miles and almost reduces, and I think eventually will reduce, the oxides of nitrogen to negligible levels. Not quite there yet. Examples of this that are being deployed and evaluated today is the Toyota Highlander hydrogen fuel cell vehicle. The first one to be deployed in the United States was in December of 2002, so 7 years ago. As a result, we've been doing this sort of a thing for a while. We now have General Motors with their Equinox vehicle through their Project Driveway program deploying 100 of these around the country to people like yourself. You could sign up and be qualified. Most of them are in Orange County of California, about 60, some in Burbank and others in the Northeast. And we have a very aggressive campaign by Honda with their Clarity, where they're also allowing the public to have access to this vehicle and to drive it. All of these applications require being able to refuel with the vehicle. And here is a refueling station that you can see with a car leaving the station, and these are now starting to be deployed in anticipation of this hydrogen future. But we need to be cognizant of where the hydrogen comes from. If we don't do that right, we'll be taking a few steps backward in improving our environment, and certainly we don't want to do that. So what I've plotted here is the carbon dioxide signature for the current automobile that is driven today, non-hybrid, and I've normalized it here to the current automobile, so on a scale of 1. I've divided it with 2 colors, a color to represent the emission from the vehicle of carbon dioxide, which we want to make 0, and the emission of CO2 from the production of fuel, which we want to make 0. One of the things I'm always reminded of when I look at this is how remarkable over 100 years we've come in the efficiency of generating gasoline. It's not only due to the 100 years of technology development, but due to the competitive forces where 88% of the gasoline that we get to dispense came out of the well. In other words, only 12% is used to extract it, transport it, refine it. And that's why this amount is relatively little. It's right around 12%. If we look now at the hybrid vehicle, like the Prius, we see the improvement that we expect, like a factor of 2, because it's like a factor of 2 more efficient. If we now take that same Prius and operate it on hydrogen, what do we expect? We expect that this carbon emission from the vehicle will go to 0 because there's no carbon in the fuel. We just showed that. And that's exactly what happens. There's no orange. But one whale of a lot of blue. And this is where we're getting the hydrogen, in this case, from natural gas, which is the go-to source today for hydrogen. It also points out why operating a car on hydrogen with combustion is perhaps not the best strategy. It not only produces criteria pollutants, but it isn't that efficient. So here you get that 16% versus 60% argument. So if we now add a fuel cell, that gets reduced, but not nearly what we think it should be, right, for this effort, this paradigm shift for the future. So we have some targets down here. We think we're going to, and already are improving, not only the natural gas production of hydrogen, but there's also substantial improvements month by month in the efficiency of the fuel cell by the competitive forces, primarily between Toyota and Honda. But we can't rely upon natural gas for our hydrogen in the future. In the United States, for fuel independence, our major opportunity at this moment in time is seen to be coal. Now, a lot of effort is being placed in coal. Coal has the highest carbon to hydrogen ratio of any fossil fuel. Natural gas, the lowest. A lot of emphasis is being placed on future power plants with coal that operate with a 0 criteria pollutant emission. That seems almost impossible, but we're pretty close. And then you've heard about capturing the CO2 from a pure stream and then sequestering it. Is a strategy to bring this down. We also have, though, the pressure on us appropriately to produce hydrogen from renewable sources, such as solar and wind, that would then electrolyze water. And that's a very attractive signature compared to where we are today. So this is starting to make maybe some sense that this is the path we should be on. And we have another renewable source from biomass that is also looking very viable for the production of hydrogen. Overall, though, our goal is to utilize as much as we can and to bring these signatures down to very low levels. And today, a lot of research is going into that objective. Now, paralleling that, we have the emergence of nuclear, which is going to play a very major role in this future as well. So that's kind of coming out of the woodwork. What I want to do, though, is show you one example. There it is, one example of some technology that's evolving. It's kind of neat, I think. That has to do with the fuel cell, and I said I'd come back to these guys up here, so I'm coming back to them. They're being deployed throughout California as an example. All these red dots here represent stationary fuel cell deployments, and we're now well over 25 megawatts, just barely hitting 20 megawatts when I put this slide together. They include, not so far from you here, so you want to visit it, the Sierra Nevada Brewery in Chico, California, where they have 1 megawatt. So each of these are fuel cell modules of 250 kilowatts, times 4 is 1 megawatt. They're being operated not on natural gas, but the digester gas from the brewery at 50% overall fuel electrical conversion efficiency. And then the waste heat is going back into the digester, where no longer do they have to have a boiler operating natural gas to support the temperature requirements of the digester. Another example is down here in the San Joaquin Valley, the Tulare Wastewater Treatment Plant. This happens to be about 900 kilowatts, almost a megawatt. In Northridge, California is the California State University, 1 megawatt. So here's a university that's actually invested in this technology, and quite a few hotels, including the Sheraton in San Diego. So this stationary activity is off and running. So you say, okay, that's great, but what's the connection to transportation? I'll give you a couple of examples before we're through. Just consider this as being a fuel cell. Right now it's at 300 kilowatts. And let's go back to our hydrogen station. One of the strategies for generating hydrogen is to pop into this space one of those fuel cells and to operate it on natural gas. We call this a station that produces electricity for a local customer, like Portland State University or condominium, providing electricity, providing a thermal product, either as heating or air conditioning, cooling. And then on demand, this is the unique technology that's just been developed in the last few years, of being able to extract off of this hydrogen in order to supply the station. This is called an energy station, and it includes the production of electricity, thermal product, and hydrogen. It is today by far the most energy efficient and environmentally responsible means of producing hydrogen 24/7. So solar and wind still are much more acceptable and needed, but they are intermittent. We have to have a 24/7 buffer, and this is emerging as being kind of the poster child for that. The way that operates, here's the high temperature fuel cell, and I'm just going to give it to you in terms of based on 100, so 100 megajoules of methane will produce electricity at almost 50%, and then produce this high quality 650 degree thermal product that can be used to drive an absorption chiller for chilling or for producing steam. This is very valuable. If we come into this tri-generation, this new technology, I want to demonstrate to you what happens by increasing the amount of energy input or natural gas going into the system by about 43%. And if I do that, I'll maintain the same amount of electrical production and the same amount of waste heat, high quality, but I will produce 43 megajoules of hydrogen at 100% efficiency. We just don't do that in engineering. But there's a synergism here in the fuel cell that gives rise to this very positive result. Now, some of you who may be studying this know that we use other technologies today like electrolysis for production of hydrogen, and the efficiencies there are just above 60%, and then steam methane formation is right around 66%, just to give you a bit of a contrast. So this should give you some hope that there are technologies evolving to help support this future. But you might say it's still operating on natural gas, that fuel cell, and you're right. Now in some states, and right now there's 13 states in the country that believe fuel cells are so magnificent they call them renewable. They're the same as solar and wind, even operating on natural gas. That's incredible from a policy point of view. Absolutely incorrect and kind of misdirected. But I want you to know that we do have states that have claimed fuel cells are renewable. But there is a way to make a fuel cell truly renewable, and that's to operate it on something else than natural gas, a renewable fuel, a digester gas from a wastewater treatment plant, or a landfill gas. Produce all of our energy streams as we had before, but now have a green energy station with green electricity, a green thermal product, and green hydrogen. Too good to be true, I think. Not really. This system is being beta tested right now in Danbury, Connecticut on natural gas after 5 years of development. And in a couple of months, it's going to be relocated to a wastewater treatment plant in California, right off the 405 interstate. Now, most of us have not seen a wastewater treatment plant and don't wish to. This is where we're treating all of our waste. And there's various aspects of it, but a key is this digester where residence time and temperature allows a lot of our waste to be broken down to where it can be appropriately disposed. But out of that comes a gas. It's called a digester gas, primarily methane, fortuitously, just like natural gas. And then it is used to go into a boiler and provide the temperature for that digester. That's the way it works today. What we can do is come in and replace the boiler with a fuel cell that not only provides the waste heat for the digester, but provides in addition electricity. Not only for the plant, but it could be for recharging in the future. So here's kind of the first taste of this connection between electrical power generation in an environmentally efficient way and transportation. But you now know that we can also produce on demand hydrogen, the second application at the connection between transportation and electricity. This particular project is due to be commissioned in October 2009, and you may want to just keep your eyes on that success. It's a strategic alliance between Fuel Cell Energy, Air Products, and the National Fuel Cell Research Center using a technology that came out of the National Fuel Cell Research Center. So example one of this nexus, transportation and electricity. The second example is dual fuel. And you've had a lot of attention this week in Portland on the electric vehicle. What I'm showing you here, you're then aware of, which is to take this Prius or this hybrid vehicle and to increase the size of the battery. And note that I'm operating this on hydrogen in a fuel cell. That makes a lot of sense. That's what we're actually anticipating, is that the future is a hydrogen fuel cell vehicle. And should the PHEV interim activity be successful, you should fully expect that the hydrogen fuel cell vehicle of the future will be a plug-in, where this battery is increased in size and then it's plugged in for getting an all-electric range of something. Rule of thumb is we would need to get 40, 50 miles of all-electric range. That's the concept. And most of us don't drive that far every day, so it means that even though we have a vehicle with hydrogen on board in the future, or in the interim gasoline, that we will be able to supply our fueling needs, by and large, with electricity. We'll also use more electricity than we would if we have an all-electric vehicle, because we'll have a backup should we run out of electricity. We've got the gasoline, or in this case, the hydrogen, to back us up. So this is what we're calling a fuel cell plug-in hybrid vehicle. This is the Toyota plug-in that we're currently testing for its future with respect to emissions, fuel economy, and social acceptance. And it is an example of a major OEM exploring this future. So it gives us some evidence that this may be on the radar of OEMs. So that's the second example of transportation electrical nexus. What happened? Nothing. I'm in full control. So I'm on slide 23 of 27. I would say it's not over. And it's not over because I just want you to take a breath here because I want to take technology one step further. Are you okay with that? All right. You recognize that? Probably not. This is the gas turbine engine under the wing of an aircraft. It's called the Brayton Cycle. Some of you have looked out the window from the terminal and see these big blades rotating. Those are the compressors that suck in the air, compress it to an elevated pressure and temperature, put it into a box that we call a combustor. We add fuel there. That's where the combustion takes place. And then that high temperature and high pressure gas comes out of the combustor, goes through a turbine that's used to drive the compressor through that shaft, and then the remaining enthalpy or energy is then expanded into velocity, kinetic energy, to provide that thrust to propel us down the runway and to our destination. So we all know this, we hear it, we watch it, it's an integral part of our lives. This technology is also the technology that's a go-to technology for producing electricity. And we do that by taking away the nozzle and replacing it with another turbine and a generator. We don't know that because we don't see that, but I'm here to tell you that that's the case. This today is the energy strategy used throughout the world to produce electricity, the most efficient and the lowest in pollutant emissions. Still has combustion. So the technology is not this. It's the fact that we have discovered in the last 10 years that we can remove combustion and replace that with a fuel cell. For you thermodynamicists, that takes away the Carnot efficiency constraint of thermodynamics and replaces it with a much more flexible Nernst potential constraint for fuel cells. And you notice that we're not only producing electricity here, but we're also producing electricity here while we are chemically treating the fuel to produce the thermal energy that we require here. This is giving rise to incredibly high efficiencies of fuel to electrical. Right now, this grid is about 35%. So coming out of the box in the first demonstration of this a few years ago, 60%. But it has the potential of getting higher. The first commercial one will be about 65%. And the optimization we're doing now is going to get us easily to 70%. And the only question is, how much higher can we get above 70%? High fuel to electrical conversion efficiency. You must remember that fuel cells have zero emission of criteria pollutants, and they're acoustically benign. So very attractive for the future, from distributed generation, like supporting the electricity of this building or hotel in the future, to a central power generation. But we're here to talk about transportation. And I must admit that we're calling this right now a hybrid fuel cell gas turbine. So this is not a Prius. This is a stationary hybrid. We need a better name, like turbo fuel cell. I like that. But hybrid is already caught on. The train's left the station. We don't know if we can pull that back. So keep your eye on this. What I want to bring to your attention, though, is the number of transportation strategies that rely upon electricity, other than the automobile. The automobile is moving to an electric drivetrain. That's the Prius. But what about other technologies? Locomotives. Those are diesel electric, operating at maybe 30% efficiency, putting out a lot of air pollutants, particularly smoke and particulate. Can you imagine repowering this with a hybrid fuel cell gas turbine? 75% efficient, more than doubling the efficiency, zero criteria pollutants. Have you thought of any others that are electrical? Oh, ships. So this portends the future of propelling ships as well. Also, long-distance trucks could very well utilize this technology for their propulsion. And you won't accept this, but aircraft. But please accept it, because both Airbus and Boeing are competing with each other in this space. Last spring at the Europe Air Show, Airbus had an aircraft there that said fuel cell powered on it. So a lot of work is being done right now with both Boeing and Airbus, not for the propulsion, but for the hoteling, the controls, the electrical, the heating, and ventilation, which constitute quite a bit of energy of the aircraft, pressurization as it flies. All of these would be operated initially on conventional fuels, diesel, probably not bunker C, but diesel, and Jet A. So there are reformation technologies that have been developed to accommodate that, to reform the fuel to hydrogen. But the future probably pretends, in my estimation, on these being fueled by liquid hydrogen. Now you may say, that's not going to happen here. But it has happened. There's been an aircraft flown by the Air Force on liquid hydrogen, and we have a major program right now with Boeing on exactly that. So it's a very serious, and if you start to look at it, it actually makes a lot of sense. So another nexus of transportation and electricity. So let's conclude with this slide. This is 27 of 27. I want to simply mention again this treasure that we are working to protect of air in our Earth system. We've talked about greenhouse gas emissions into that atmosphere. We've talked about criteria pollutant emissions into that atmosphere. I brought something to your attention I really want you to think about and start watching the literature for the first evidence of measurements of the reduction of the concentration of oxygen in the atmosphere. That's going to be a remarkable wake-up call to the public. But we've also talked about this nexus of transportation and electricity. And I'm going to conclude by saying we also have another important nexus, and if I didn't mention it, it would be irresponsible, because it has to be on our agenda, which is water. The utilization of water to produce these alternative fuels. In many cases, it's huge, and it's got to be near zero, if not zero. In the energy regime, well, even before I get to that, let's just open this up and look at the amount of water we have on the Earth. After a few days of viewing this, I began to absorb that. The atmosphere is 10 miles thick. Earth is 8,000 miles in diameter. I'd probably come up with a volume like that for air. But when I saw this for water, I said, that's not possible. That must be only the potable water. And it's not. It's the seawater, the potable water, the river water, the Willamette water, the ice caps. It's still hard for me to accept that. So I challenge you to verify that. But that's a smaller resource even than the air. And in energy, we have a very strong interaction. It takes water to produce electricity, and takes electricity to convey water. Today, in most states, California, 20% of our electricity goes to water, and 34% of our natural gas goes to water. So water is a big part of the equation. Of course, it's a big part of what we require. As a result, the powering of the future transportation will depend upon all of us keeping into account these resources that we need to protect and maintain, as well as to assure that their health is sustained. And with that, let me thank you.
Remember to use the microphone if you have any questions. Have it portable if your microphone doesn't.
Well, the gentleman way in the back.
Dr. Samuelsen,
Oh, do you have a microphone?
Interesting and captivating presentation. And I guess I have probably as much a comment as a question for you and for my fellow participants. And that is that you began with looking at the the slides from California from a policy and scientific perspective on where we need to be in the short term in terms of reducing our CO2 emissions. And a lot of these technologies seem to be far into the future in terms of meeting those goals. And so I guess I just want to make a statement, which I'd like to hear if you agree with or not, that the technology is going to help us, but it's not going to save us. And if we're really going to meet our CO2 reduction goals, we're going to have to look at our consumption of what we have right now. And in terms of transportation, that's a lot on the transportation demand management side.
Fully agree with you 100%. And on that slide where I had the paradigm shifts, you saw right in the middle I had conservation. That wasn't at the end, wasn't quite at the top, but it was right there. You might even think of that as a heart of the strategy that has to be kicked off immediately and pushed as hard as we can. There was a question here.
Can you comment on the life expectancy of the high temperature and low temperature fuel cells and also their toxicity at the end of their life? The high temperature fuel cells, let's take and the question is their lifespan. The phosphoric acid fuel cell from UTC has been commercialized for about 15 years and has demonstrated life easily on the order of about 10 years. The current product being produced by UTC comes out of the box with a 10-year warranty, and with a service contract 20 years, and that's really good. I mean, that's a nice evolution in the stack technology, so we're very pleased to see that. The molten carbonate fuel cells produced by Fuel Cell Energy come out of the box with a replacement after 5 years already bought to give you 10 years. So the stack is well beyond 5 years, but not much beyond. We need to get to 10. And that's where that technology is at. And both of those work well for this continuous baseline operation 24/7. The small fuel cells, the proton exchange membrane, have a life that's more like a year. And that works okay for the automobile because the off-on over 10 years of the life of the automobile, that PIM will only be used about a year. So that works okay there. And it works okay in stationary applications where the PIM can be used as a backup, where it's only called upon periodically to provide power, like for a telecommunication tower. But there is the hope that the life could be longer so we can have that kind of a fuel cell in our home. And there is a new product by Plug Power called the GenSys Blue that offers at least 2, maybe a bit more years. So it's not 5, it's not 10, but it is an improvement. And whether or not the PIM is successful in the stationary market for continuous operation, we'll have to just wait and see, but it's definitely already there for backup power, 1 year going on 2 with respect to stack life. On the toxicity, that's a point of very important attention to us because this is a chance with a new technology to do it right, which means life cycle analysis. So we're watching the materials that are being used like a hawk to assure that not only are the residual materials after the life of the system not toxic, but that we can recycle if the majority of the materials. That would be the cradle to cradle sort of concept. Not exactly there yet, but the fact that we're putting attention on it, the agencies are starting to recognize that, gives me great hope that we'll be able to achieve that. We need to. Yes?
So you talked a lot about, all the things that the U.S. is doing. This is obviously a global problem. How are other countries contributing to this technology and helping us advance? A lot of aspects of that, so let me give you some examples. In general, a very substantial attention with other countries, especially in Southeast Asia and in Europe. We have in the automobile fuel cell, Toyota and Honda competing with one another, and Hyundai out of Korea not doing so bad either to push the U.S. to a much greater level of technology than we have today, as an example of Southeast Asia. In Europe, we have the Scandinavian countries Denmark is an example working toward a very high percentage of deployment of renewable for electric power generation. There are very strong companies in Korea. There's actually a steel company called POSCO that is taking a U.S. product, this molten carbonate fuel cell, and deploying it proactively around Korea and starting to become a distributor for Southeast Asia, even ahead of the U.S. market for stationary power application. Spain is working to become a lead in the European Union in the advanced stationary power generation technologies, so on and so forth. So just a very substantial amount of activity, and also refreshingly, universities, especially the last few years, are coming out of the woodwork to create programs in this space. They were not seen a few years ago, but now we have center this, center that, institute this, and that's very refreshing for the workforce of the future as well. Right here.
You said these fuel cells use natural gas. I wonder, is it really possible to replace natural gas by landfill gas and digester gas in terms of the amount we can produce landfill gas or digester gas?
Are you able to hear that in the back? Well, the question is, if the large stationary fuel cells operate on natural gas, can they really operate on digester gas and landfill gas that have a lot of contaminants in them? Let me first say that the proton exchange membrane fuel cell, the small one for automobiles, requires very high purity hydrogen. And if you try to operate one of those on natural gas, which has been done, it takes a very substantial reformer and cleanup process to get that purity. The larger fuel cells don't require as pure of hydrogen. And as we go up our chart, the requirement becomes even less. They can operate not only on hydrogen, but on carbon monoxide as well, which for the PIM is actually a poison. Already today, there's a deployment of about 7 megawatts, which would be about 28 high-temperature fuel cells in California operating on digester gas. So it's being done today. And there's about 7 projects currently under construction. And that's because a fuel conditioner, and maybe you saw it on my slide, I had a little box that came in along with the high-temperature fuel cell. It's a conditioner. That technology has now been established and works very well for a long-term operation of a fuel cell and a digester gas to take out some of the contaminants that would otherwise affect the fuel cell operation. Landfill gas is much greater in quantity and a much greater resource than digester gas, at least in California. So we really have eyes on that. But landfill gas is very different than digester gas. Digester gas knows what you're going to be producing every day. It's pretty well known what you're going to be sending down the sewer. But the landfill doesn't know really from day to day what you're going to put in or what was put in 8 years ago. So it comes forth with all sorts of things plus methane, which is what we want. And the technology for cleaning that up is being addressed, not with great intensity yet. It's pretty straightforward to address it, so it will be addressed into a greater extent, and probably within a year and a half we'll have the first deployment at a landfill. Remember the credit. One more question here.
I was wondering, when the fuel cell stations are available, meaning all cars are fueled by fuel cells, is there any idea of the projected price per gallon of the hydrogen fuel cell fuel?
So what will be the price per gallon of hydrogen? If you go to the pump at our station, it says $4.99 per kilogram. The goal would be to make that eventually right around $3 per kilogram. But let's just take $5 per kilogram that we're charging today. That translates into $5 per gallon, because a kilogram is like a gallon. That seems like exorbitant. But remember these efficiencies here. The fuel cell is going more than 2, almost 3 times further on that $5. So the equivalent cost to you is let's not go to 1/3, let's just take 1/2 of the $5, $2.50 per gallon. That's not bad. Now, the next question is, what are you actually paying, Professor Samuelsen, for that fuel? And I'm paying $12 per kilogram for it. And I'm subsidizing it $7 per kilogram. So the actual cost today from purchasing it from a hydrogen supplier is right around $9 to $12 per kilogram. But that's within a factor of 2, which would make it that's pretty good. And the technologies that are evolving are going to easily be able to get us into better than a gasoline price today. And if you think about Hubert's curve going up there and hitting that peak of where gasoline will be going in not too so many years, $12 per kilogram is probably going to be attractive. And if you consider the first comment made in back of working toward conservation and less use of the car, maybe we need $12 per kilogram or $12 per gallon in order to cut our use of the automobile today from what it is today. How are we doing on time? One more question, or is that it?
I think you want to end with 2 web questions.
Oh.
So they're sort of related. One, can you comment on the safety of hydrogen as a fuel in automobiles? And 2, are you aware of any current federal or state initiatives to develop hydrogen sort of fuel distribution infrastructure?
Short answers, right? Well, the first one on safety, the University of Florida crash tested 2 vehicles, one gasoline, one hydrogen. And if you saw the film, you'd say, I definitely want to be in the hydrogen vehicle. The reason is that the gasoline pooled around underneath the vehicle, caught fire, and the occupants, which were dummies in this case, were trapped. The hydrogen vehicle, the hydrogen tank pierced, so it also was penetrated. But hydrogen, because it's very buoyant and very diffusive, went straight up and away from the passengers. So while that's good, we also have some concerns. One concern is that hydrogen going up, if it ignites, you can't see it. That's not good. And so getting some means of having a color in that, much like we put an odorant in natural gas, needs to be seriously addressed. The second is that in your garage, if there's a hydrogen leak, you won't smell it, and you won't otherwise be aware of it if there's not a sensor. And in our garage, of course, we have ignition sources, the water heater, the clothes dryer. Now, over many years, we're comfortable putting a gasoline car with 20 gallons in our garage with those same ignition sources. So over the years, there's been this evolution of codes to handle that. We don't have that quite yet for hydrogen. And although it's very diffusive and will get out of the garage very fast, we really have to have, I think, substantial ventilation and some backup sensors, and probably also an odorant for hydrogen, which we don't have today. So those are all addressable, but they haven't yet been addressed, so very fair question. On the second one, there is just completing a infrastructure initiative by the Bush administration from his announcement in the State of the Union address in January of 2007 of investing about $500 million in infrastructure that has had its effect around the country. And then the state of California has put about $2 to $3 million a year toward hydrogen infrastructure as well. But that's a drop in the bucket, but it's a big drop. There's a need for additional investment, and once that investment is made, the automobiles will come. In fact, the automobiles are already coming, and the energy companies need to start to respond to that and start to see that there's a business enterprise here where their own personal investments will work. This is a big question, so let me just conclude by saying that there's a Assembly bill in California, AB 118, that is going to invest $120 million a year per year for 7 years in alternative fuels and alternative vehicles. And just last week, when they put out their plan called an investment plan, they said we're going to initially dedicate $40 million to hydrogen infrastructure. We'll see if that holds up, but it's the biggest contribution outside of the federal one that has been made to date, certainly the biggest by any state. if that's it, I thank you all very much for your attention. You've been an outstanding audience. Thank you.